The skill assumption, over-reliance on perception skills in hazard analysis. Welcome to this presentation. My name is René van Paasen. I am an associate professor with the Faculty of Aerospace Engineering of the Delft University of Technology. Today's presentation is about the importance of perception skills in flying, not only manual flight but also when operating aircraft through the autopilot or flight management system, and how we might take these skills for granted in the design of aircraft systems and procedures. This work was inspired by the events with the Boeing 737 MAX. We don't offer a new analysis, but try to provide some insight that might teach us a more general lesson on the role of perception skills. There have been 2 crashes with the Boeing 737 MAX. Understandably, these crashes have received a fair deal of attention, coming close together, having the same initiating event, and involving new aircraft from the latest 737 model. With the advantage of hindsight, it is now known that these accidents would have been survivable if the pilots had only flipped the trim cutout switches, and then maintained careful elevator trim and speed control for the remainder of the flight. Several people I talked to at the time in Delft and at Penn State, where I enjoyed a brief sabbatical, were at least attributing part of the blame to pilot error and pilot inexperience. However, we should try to understand what makes it likely that pilots fail to successfully start the appropriate checklist in these scenarios. By now, investigation into the first of these crashes have been concluded, resulting in many recommendations and modifications, while the 737 MAX was grounded until it could be recertified to fly. The main trigger in the crash of Lion Air Flight 610 was a signal from a faulty angle of attack sensor. This sensor indicated a high angle of attack on the captain's side, while the sensor on the co-pilot side was functioning normally. Early in the flight, this led to several events. A speed disagree message, a difference in the indicated altitude between the captain's and the co-pilot's instruments, a difference in indicated airspeed, an airspeed low message, an indication of excessive airspeed on the captain's instruments, and the activation of the stick shaker that normally indicates a stall. In short, a whole slew of problems. A little later in the approach, the takeoff flaps were set to 0, while the captain was hand flying the aircraft. At that point, the MCAS system activated, sending nose-down trim commands to the trim system of the horizontal stabilizer. The MCAS system is the Maneuvering Characteristics Augmentation System. It was added to the 737 MAX design when it became clear that the large engines installed well forward of the wing had the potential to pitch the aircraft nose up at high angles of attack. The system uses the input of an angle of attack sensor and produces a nose-down trim action by sending a 10-second nose-down trim command to the trim motor, which changes the angle of the horizontal tailplane. The effect will be that the airplane pitches its nose down. MCAS is only active in manual flight and when the flaps are up. That is why it did not activate right after the start. The pilot training for the 737 MAX did not include information on this system. Boeing designers had assumed that the runaway stabilizer or runaway trim procedure, which was in the checklists of all 737 models, would enable pilots to cope with a malfunctioning MCAS system. So, if Boeing assumes that MCAS failure can be handled as a runaway trim, let's see what that is. Back in 1984, as a young trainee, I was asked to analyze video recordings from test flights with the Swearingen Metro at the Dutch National Aerospace Laboratory, NLR. There were several runaway trim incidents in this footage. After a pilot used the trim switches, the electric trim motor would not stop, but continue running. It was caused by crappy switches that don't properly release. On my videos, pilots handled this with ease, swiftly identifying the problem and using a circuit breaker to cut the power to the trim motor. This type of trim runaway was still an issue when the 737 was first introduced, back in 1967. However, more reliable technology means that nowadays a classical trim runaway on a modern airliner is very rare. Here is the runaway stabilizer checklist that should support pilots in stopping a runaway trim or a rogue MCAS system. Pilots need to know these actions by heart. But once this work has been done, flying becomes a lot more work because hand trimming a B737 is tricky. The thing to note is the condition for starting this checklist. Continuous uncommanded stabilizer trim. This matches the original faulty trim switches. It does not match MCAS but produces trim in bursts, and in this case in a direction opposite to what might be expected with a stuck trim switch. In addition, there is Boeing's speed trim system installed since the 737-300, which always and automatically helps in keeping the aircraft trimmed. It also produces trim bursts, not unlike MCAS does, only under slightly different conditions. Reaction to erroneous MCAS activation needs to be swift. In his book Thinking Fast and Slow, Kahneman describes different mechanisms in the human brain. Fast thinking with instinctive, associative, immediate reactions versus more laborious reasoning. Danish researcher Jens Rasmussen distinguished 3 levels of human behavior: skill, rule, and knowledge-based behavior. In his works, he uses various diagrams to illustrate that split. This is one of the simplest. When I asked my students for examples of these levels of behavior, they would maybe come up with riding a bike, performing a checklist, and writing their thesis. That is correct, but their answers typically focus on the observable action side of things. Here at the bottom left in Rasmussen's diagram is a feature formation block, which provides the input for rule-based and knowledge-based behavior, essentially starting Kahneman's fast and slow thinking. Rasmussen labels these information paths with sign and symbol, and the block is placed squarely at the skill level. This is the function that enables humans to detect events or features from the barrage of sensory input. It produces our knowledge on the world. For example, in symbols, that the fuel tank is indicating a certain level. That means, for action, it's a sign that it's time to find the gas station. This feature formation is a skill. It must be trained as such, by practice with situations that produce the actual or at least sufficiently representative sensory input. Studying with a book or an electronic tablet allows a pilot to memorize the checklist and reproduce it on a test, but it does not train the feature formation. In this case, with the MCAS activation pattern being new and hidden in a mountain of other sensory input, and without experiencing this in training, pilots in the accident scenarios fail to make the connection to the runaway stabilizer checklist in time. In other words, their sign didn't arrive. Pilots in the Lion Air crash did not use the cutout switches, and in the Ethiopian airline crash used them at a moment when the airplane was already severely out of trim. Boeing designers were probably correct in assuming that the items on the runway stabilizer checklist enable pilots to handle erroneous MCAS activation. However, they did not foresee that pilots would not be likely to have the feature formation skill necessary for recognizing the trigger condition. Rasmussen's model emphasizes that skill is not only the capability to perform action, but also the capability to extract meaning from sensory input, which is an aspect of skill that we tend to take for granted. Like other types of skill, it cannot be trained by studying, only by hands-on experience. And note that the importance of feature formation skill is only going to increase as we have more advanced automation. As mentioned in the introduction, this is not a drastic new insight on the MCAS accident, but hopefully it sheds some light on how even experienced pilots can fail to initiate the proper checklist actions. The main message is that we must not forget that there is skill involved in extracting the right meaning from sensory input. The skill requires training, similar to learning to ride a bike, with lots of trial and error and relevant conditions, and for this case preferably in a good simulator. We as designers tend to overlook this skill and assume it magically happens, However, anytime you foresee that an immediate reaction will be required from flight crew or operators, in other contexts, we should make sure that people can train the skill to detect the start condition for this reaction. Do not assume that people under time pressure can put together the pieces cognitively by reasoning and thus with slow thinking. Give them an opportunity to refer to previous experience. Thank you for viewing this presentation. For more information, you can read the paper we wrote on this topic. I look forward to your reactions and hopefully we can discuss this live on the conference.